Welcome to Chapter D on Cosmology. In part one of this video lecture, we will be looking at the Big Bang Theory. So up until now, in our study of astronomy in this course, we have been looking at individual objects inside of the universe. For example, we studied planets, we studied stars, and we studied galaxies. But now what we're going to do in the study of cosmology is look at all of this stuff together and look at the universe as a single object. So cosmology is the study of the origin, structure, and evolution of the universe as a whole. A good place to start with our study of our universe is to think about the question, can the universe have an edge? So let's assume that somehow the universe did have an edge and it didn't just keep going on and on. What would this boundary or edge be made of? Obviously, we don't expect to see a brick wall at the end of the universe if we were to go out there in our hypothetical spaceship. And even if it weren't a brick wall, if there was some other kind of boundary, the question comes up, what would be on the other side of that boundary? Well, if there's a boundary, that implies that there's something on the other side. But space, and in particular the universe, must be everything. It must include everything, therefore it can't have a boundary or an edge. So this leads to the so-called edge-center problem. How do you find the center of something? Well, you have to use the edges. So for example, if you have a pizza here, and if I were to ask you, where is the center or the middle of this pizza? You would probably point somewhere right around here. Now the reason that's easy to do is because you're using the outside edge of the pizza to define the center here. Likewise, if our universe had an edge around it, then we could define the center of the universe. However, remember that space cannot have a boundary or an edge, therefore it can't have a center either. So this is sort of a non-mathematical proof. Basically, we're just using logic here to state that there can be no center of the universe. We introduced Edwin Hubble, the American astronomer, in one of the previous chapters here on astronomy. He had several important discoveries, but for this chapter, the main one that we're concerned about is he discovered the expansion of the universe by plotting galaxy speeds as they speed away from us versus distance from us. And this led to what is now called Hubble's law, which says that the farther away a galaxy is, the faster it is moving away from us. And Hubble was able to interpret this physically as an expanding universe. And we're going to look at this in a little more detail so that it's very clear and you'll be able to understand what Hubble's law is all about. Mathematically, though, Hubble's law, if we were to plot a bunch of galaxies like this, we saw this plot in the last chapter. This is distance from Earth down here. And, this distance is usually measured in millions of light years, cosmic distances. And this axis here, in the vertical axis, is the recessional velocity, which just means how fast is that galaxy moving away from us. And when Hubble plotted a bunch of galaxies and put them on this graph like this, he found out that they have a very distinct pattern or relationship here. In other words, they're not just random points all over the graph. They follow a definite trend here. And the trend is simple. It says that the farther away the galaxy is from us, the faster it appears to be moving away from us. And by the way, the slope of this graph is called Hubble's constant, h0, which we'll talk about a little bit later. So, if the universe is expanding, let's see what this really means. It says that on large scales, the galaxies are moving apart with a velocity proportional to the distance. One of the kind of subtle things about the expanding universe is that the galaxies are not technically moving through space. They're actually sitting still. what's happening is the space between the galaxies is expanding, and that carries the galaxies along. And so there, the effect or the outcome is kind of the same, but it is a subtle and important difference, and we'll talk about this a little bit later as well. But kind of what we mean here is if we take a section of the universe sometime in the past, let's say this big cubic region of the universe, and it's got these 4 galaxies inside of it, then later on in time, this same region of space will have expanded. Notice the space is now larger of the box, but the galaxies inside it are not expanded. They're still the same size, but notice they're farther apart. So these galaxies are moving away from each other, even though they're technically not moving inside the box. They're staying in the same position. It's just that the box has gotten bigger. One great way to explain the expansion of the universe and Hubble's law is something that's very simple to imagine. It's called the raisin bread model of the expanding universe. So our analogy here is we're going to bake a loaf of raisin bread in the oven, and the dough will expand, taking the raisins with it. So let's see how this works. Let's imagine we take our unbaked loaf of raisin bread here, and if we were to look inside, we see several raisins just sort of randomly distributed amongst the dough here. All right, so then we take this raisin bread dough, put it in the oven, and let the whole thing expand. Okay, so what happens when we're baking this thing? Well, the bread expands because of the yeast and all that stuff in there. So what happens to the raisins? Well, the raisins, of course, are still raisins. They don't expand. But notice the raisins are all farther apart from each other now because the bread has expanded. So let's take a look and see what happens if we were to consider ourselves maybe as a tiny little insect or ant or a tiny little shrunken person on one of these raisins. So each raisin sees its neighbors moving away from it. So if we're on this raisin right here, we see all of these raisins moving away from us. They're all going directly away from us. So each raisin feels like it is in the center of the expansion because this raisin sees every other raisin moving away from it. But we could do the same thing for this raisin right here. This raisin sees all of these neighboring raisins moving farther and farther away from it. So this raisin would also feel like it's in the center of the expansion and everything's moving away from it. That is correct, but every raisin can say the same thing. Now, here's where Hubble's law comes into place. The farther away the raisin, the faster it appears to be moving. So let's take this raisin again here as our reference. Let's imagine we're on this raisin. By the way, these raisins represent galaxies in the universe, and the bread represents the space between the galaxies. So for this galaxy or raisin right here, let's take a look at this raisin that's very close by. Notice this raisin here, which is right here afterwards, has not moved very far. All right, because there wasn't much bread or dough in between these two raisins to expand. So this raisin will appear to be moving very slowly away from our reference point here. If we bake this loaf of bread and it takes an hour, this raisin's only moved a tiny bit over that hour of time. But now let's take a look at, for example, this raisin here, which is much farther away from our reference raisin. Well, look at how far this raisin has actually moved. It's moved quite a bit farther. It's gone from about here all the way over to here. So it's moved a farther distance in the same amount of time. Therefore, it appears to be moving faster away. And if we look at, for example, the extreme is this raisin down here. This is the farthest one from our reference raisin here. Look at how far it is moved over here. It's way down in this corner. It's moved, from basically about here all the way over to here. So this raisin will appear to be moving the fastest. So this is Hubble's law. The farther away the raisin or galaxy, the faster it appears to be moving. Now, remember, the key thing here is that the raisins are not moving through the bread. They are moving with the expanding bread. So this, raisin right here has not actually moved through the loaf. It's still in the same position in the loaf. It's just that the whole loaf of bread has gotten bigger, so it was carried along with that. So this is a key and kind of subtle point about the expansion of the universe. The galaxies are not moving through space. They're actually just sitting still, but they're moving with space, which is expanding. So from our point of view on this galaxy right here, it appears that all these galaxies are moving away from us. They are getting farther and farther away, but the galaxies themselves are not actually moving. They're just traveling along with expanding space. So all of this leads us to something pretty remarkable. From this, we can come up with the necessity for the Big Bang. So if the universe is expanding right now, and it obviously is based on Hubble's data and lots of other data since then the universe must have been smaller in the past. So what happens if we keep running the clock backwards all the way to the beginning? So if this is our present universe today, and we're going to just represent it sort of like by this bubble, we can sort of think of this as ourselves in the center here, and this is as far out as we can see. This is the observable universe. Well, then sometime in the past, this section of the universe here was smaller, right? All the galaxies were closer together. Just think of the raisin bread going backwards in time. So if we keep going backwards in time, the universe gets smaller and smaller and smaller until we finally reach a point when basically this portion of the universe right here has no size at all. And this is literally what we call the Big Bang. So the idea of the Big Bang is that if the universe is now expanding, then in the past it must have been smaller. Extrapolating backwards in time, the universe must have once been compressed into a high-density, high-temperature state called the Big Bang. The Big Bang is not really an explosion, as the name says, because what did it explode into? Well, nothing. There was no space outside of the Big Bang. In fact, the whole name Big Bang was sort of suggested to poke fun at this theory of the origin of our universe. One of the earlier astronomers that believed that the universe had always existed and didn't burst into being, he said that, basically what you're trying to explain here is that the universe all of a sudden popped into existence with a Big Bang. And he was actually mocking the theory. But it turns out that the theory, as we're going to learn, has all physical evidence supporting it. Now, there's some interesting and very difficult questions that go with the Big Bang theory for the origin of our universe. We already reasoned that the universe has no center, right? Remember, the universe doesn't have an edge, therefore it can't have a center. So in this sense, the Big Bang did not occur at a single point. The Big Bang occurred everywhere at once. And, this is not easy to obviously visualize. One of the questions that comes up is, well, okay, if this is all well and true, then what caused the Big Bang, right? We're in a science class and we like to think of the universe in terms of cause and effect. So what caused the Big Bang? In other words, what was before the Big Bang? Now this is, again, these are interesting and very, very difficult questions. The conventional theory says that the Big Bang was the birth of space and time itself. So there could not be anything before the Big Bang. So some cosmologists will just sort of argue that it's senseless to ask about things before the Big Bang. If there wasn't any space and there wasn't any time, then there was nothing before the Big Bang. So you're not even allowed to ask the question. And that's not a very satisfying answer, of course. So some other cosmologists have proposed some alternate ideas that I'm going to briefly show you, just kind of for fun, but we really don't have any evidence for these alternate ideas. All the physical evidence that we have supports the Big Bang, but it doesn't tell us anything about what happened before the Big Bang or what actually caused the Big Bang. And so this will hopefully become more clear. But let's take a look at some of these alternate ideas. One of them is called the cyclic universe model. And this kind of treats our universe as a three-dimensional membrane. So our three dimensions of space are represented by a membrane. And here is our present universe, this sort of wrinkly looking thing here. And our universe is actually separated from another three-dimensional membrane universe by a fourth dimension that we can't detect, or we can't basically, we have no perception of it in a sense. Now, when these membranes originally collided and separated, that was the original Big Bang here. So these two membranes are separating with time. But according to this model, they will actually come back together at some point, and when they collide, it'll cause another Big Bang. So this whole process here is a cycle, and that's why it's called the cyclic universe model. But the problem here is, unless we can find, evidence for this other sort of parallel universe here, then it's really not a scientific theory per se. And at this point in time, we don't really know how we can gather physical evidence to say this can actually have happened. And remember, that's sort of the crux of science is based on physical evidence. Another model that has actually gotten quite a bit of traction recently is called the multiverse or bubble universe model. And this one has its roots in quantum physics, which is something we didn't really talk about much in this course. It's a pretty advanced topic. But the idea here is that quantum fluctuations continuously cause new Big Bangs to pop into existence. So the result is a vast multiverse consisting of numerous bubble universes. So our universe is represented by this bubble right here, but we can see there are many other universes, and more are continuously popping into existence. The last sort of far out model here that I'm just going to mention that cosmologists are talking about and researching is this one called loop quantum cosmology. And basically the crux of this one is that there was a pre-existing universe, and over time it collapsed due to gravity to a single point, and then it began expanding again. So this is the Big Bang. Actually, here they call it the Big Bounce, because it's a pre-existing universe that basically fell in on itself, collapsed, and then bounced back into what we call the Big Bang, into our present universe, which is over here. So this is sort of like a timeline going from here to here. We're in present time, we're out here. All right, let's get back to something we can actually talk about with confidence and with physical data, and that is our present universe. We may not know what caused the Big Bang or what was before the Big Bang, but we certainly have a lot of physical evidence that supports the Big Bang theory and what has happened since the Big Bang. That is a fairly precise scientific study, and that's what we're going to highlight in this video here, and also in part 2 of this video later. So one thing we can do immediately is actually do a very kind of quick and dirty estimation of the age of the universe. So if we know the current rate of expansion of the universe, and if we make an assumption here that the expansion rate hasn't changed, that it's always been expanding at the same rate, we can kind of do a quick estimate of what the present age of the universe is. And it's surprising that even though this assumption here is not really accurate, but we're still going to get a result that is very close to the more precise result. So, and it just takes a couple steps to do this. So let's start with Hubble's law. Remember, Hubble's law says that the velocity of a distant galaxy moving away from us is equal to the Hubble constant times the distance to the galaxy. So v, velocity, equals h, Hubble constant, times distance. And the current value for the Hubble constant is a little bit under debate, but all of the values that are currently believed to be accurate are somewhere around 68 to 70, low 70s in terms of these strange odd units, kilometers per second per megaparsec. So what I'm going to do is use the number 68 here, because that was a recently a pretty well-established number for the Hubble constant, and convert this into inverse seconds. So I'm not going to show all the steps here, but kilometers per megaparsec, that can be converted. And these two distances, a kilometer and a megaparsec, are distances. They actually sort of cancel each other. And what we're left with after we convert kilometers to megaparsecs and so forth and cancel everything is, here's a number for the Hubble constant in terms of inverse seconds, seconds to the -1. So it's 2.2 times 10 to the -18 inverse seconds. Now, we know from earlier in the course that, remember when we studied kinematics, velocity is equal to distance divided by time. So v equals d over t. And therefore we can solve this for time, and we have time is equal to distance divided by velocity. This is something we did way back in chapter 3. So let's take this equation, time equals distance over velocity, and for velocity here, let's substitute in, from Hubble's law, velocity of a galaxy is equal to hd. So we're going to put hd down here. So basically what we're doing here is we're finding the time it takes for the universe to expand outward to its current distance. And what happens here is these d's, the two distances, cancel anyway. So the time, which is called the Hubble time, by the way, is just 1 over Hubble's constant. So, you know, this can be done on your calculator. 1 divided by 2.2 times 10 to the -18 is, you know, this is a very small number, obviously, but when we divide by that, we get a very big number. So we get 4.5 times 10 to the 17 seconds, and we can convert this into years, you know, by doing, there's 60 seconds in a minute, 60 minutes in an hour, let's see, and there are 24 hours in a day and 365 days in a year. So by doing all those conversions, this number here translates to approximately 14 billion years. And this so-called Hubble time is surprisingly close to the more accurate age of our universe determined by cosmologists and their data, which is about 13.8 billion years. So you know, amazingly, just by doing a couple quick steps here, we can estimate the age of our universe since the Big Bang quite accurately. And the age of our universe is approximately 14 billion years. Remember, when we talk about telescopes, one of the fascinating things about using telescopes is that they are like time machines, in that when we look out into space, we're actually looking back in time, because it takes light a finite amount of time to get to us. And so the farther away the object is, the more it took, you know, the more time it took for that light to get to us. Therefore, we're basically looking farther and farther back in time. So if we look at this diagram here, let's place ourselves, our Milky Way galaxy, right in the center here. And so what this graph shows is that as we look out in any direction from our home here on the Milky Way, we're looking back at time. Well, if we could look back 14 billion years or so, in theory, we should be able to look all the way back and actually see the Big Bang. And so that's kind of what's represented by this outer horizon here, is this represents the farthest back we could possibly look, which would be to the beginning of the universe 14 billion years ago. Now, it's not quite this straightforward, and it's unfortunate that we can't look back and actually see the Big Bang with any clarity like this, because the early universe wasn't actually transparent, because it was so dense. Remember, right after the Big Bang, the universe was in this very hot, very dense state, and light didn't actually travel through the early universe. But we can see back to almost the edge of time. We can see back about 99.997% of the way to the Big Bang. The first few 100,000 years of the universe was so hot that it wasn't it wasn't transparent. And so we actually can only see back to a few 100,000 years after the Big Bang. But that's what this circle represents this shell around our field of view. This is the early universe that we can actually see. We can't see to the Big Bang itself, but we can see almost to the Big Bang, and we should be able to see this early, hot, dense state of the universe, and indeed we can, and we'll be talking about that next. So the radiation from the Big Bang, if we could look back far enough, as we just explained on the previous slide, then we should be able to see the hot, dense, early state of the universe. And in fact, this radiation that's given off by the early universe is called the cosmic microwave background radiation. And it's still detectable today. In fact, it was discovered sort of by accident by two communications engineers at Bell Laboratories, the telephone company. Back in the 1960s, Wilson and Penzias were tasked to try to find the source of some static and hissing that was heard on long-distance telephone calls. And these calls were sent basically through space using these big antennas, and they were sent as microwaves. These are communication antennas, basically. So they were trying to figure out why all the long-distance telephone calls had this sort of annoying background hiss. And they couldn't figure out what the source of it was. They thought, it might be interference from something on Earth. They ruled that out. They even thought it might have been due to pigeons that were nesting inside of this antenna and pooping all over the antenna. So they went in there and they scraped out all the pigeon poop, but it was still there. That hiss was still there. Well, it turns out that and they eventually found out what they actually were hearing was basically leftover radiation from the Big Bang itself. And this is called the cosmic microwave background radiation. So they ended up winning the Nobel Prize for this discovery. It is arguably one of the most important discoveries ever made in the field of astronomy because they found physical evidence for the Big Bang itself. When this radiation is plotted, this is the wavelength of the radiation down here versus its intensity. It has a very characteristic curve here that physicists knew about long before this discovery. And this particular curve is called a blackbody radiation curve. And the peak of this curve can tell us the temperature of the body that's emitting the radiation. So what the temperature is in basically today is this graph tells us the temperature of the universe, and the temperature comes out to be 2.73 kelvins. So, keep in mind, this is extremely cold. This is the temperature of the current universe. All right, not the temperature during the Big Bang, but the universe has cooled since then to this temperature of 2.73 kelvins. By the way, remember that 0 kelvins is called absolute zero, and that is the coldest possible temperature. So this is saying that the universe today is obviously very cold still. So just to kind of clarify, what is this cosmic microwave background radiation, or CMBR, that these two guys discovered and won the Nobel Prize for? One way to think of it, sort of loosely, it's the echo of the Big Bang that happened 14 billion years ago. It's the first and oldest light in the universe. And interestingly, this light is still shining through the universe today and can be picked up and detected today by any astronomer with a radio telescope or an antenna. The CMBR originated from the hot gas of the early universe. The expansion of the universe stretched these photons to a wavelength of about 1 millimeter, which are now microwaves. So that's how they detected them in the microwave. The temperature of the universe has likewise cooled since the Big Bang to 2.7 degrees kelvins, and this is the measured temperature of the universe today. So the CMBR, this cosmic microwave background radiation spectrum, matches precisely this 2.73 Kelvin temperature. So one way to think of this is the CMBR is like a smoking gun in terms of physical evidence for the Big Bang theory. This is kind of an interesting graph that attempts to show the entire timeline history of our universe from the Big Bang over here, and this is time down here, all the way up to the present time. Now, this is not a linear scale by any means. For example, the first part of the graph here, these are seconds, and then minutes, then hours, then days, finally years and centuries, and then we have millennia, and then by the time we get to the end, we're talking about billions of years for each tick mark here. But what this is plotted here is the temperature of the universe going up here. And so this red line represents the temperature versus time of our universe. And the idea here, there's a couple of main ideas. First of all, it shows that the universe basically started out very hot, and over time the universe has cooled to its present temperature of about 2.7 kelvins. But what else, the other things that this graph shows are key events that happen along the way. So for example, at the beginning of time, we have the Big Bang itself. Within the first few seconds, the fundamental particles of matter started to form. Protons, neutrons, and electrons sort of fall out from the initial energy of the Big Bang. And this is something that particle physicists can model and explain with great precision, how energy can actually sort of congeal to form these particles that make up atoms. So within the first few minutes, hydrogen and helium nuclei begin to form, and then after we see actually quite a bit of time go on here. After a few 100,000 years, the first atoms form. The electrons start to attach to these nuclei, and this is when hydrogen and helium atoms form, and this also marks the time when the universe actually became transparent. So we can actually see back to this region right here, which is called recombination, and it occurred about 380,000 years after the Big Bang. After that, the first stars begin to form. They begin to produce heavier elements, and then the formation of galaxies starting, this is roughly 10 billion years ago. The galaxies started to form and are still evolving today at the present time. So this whole graph here, is roughly 14 billion years of cosmic history, all shown on one page. And these are some of the key events that happened along the way to get from the Big Bang to where we are today. Let's end this part of the lecture on the Big Bang with just a summary of the key pieces of evidence for the Big Bang theory of the origin of our universe. So again, what is the Big Bang theory? Well, the Big Bang theory explains how our universe basically came to be. So there are several pieces of physical evidence that support the Big Bang theory and led to its formulation. So the expansion of the universe due to Hubble's law, remember, if we extrapolate our expanding universe backwards in time, we come to a hot, dense beginning, which is the Big Bang. The cosmic microwave background radiation, that's the echo of the Big Bang that those two engineers discovered, and it matches the predicted spectrum precisely, and the current temperature of the universe being just 2.7 kelvins comes from that as well. One thing we didn't talk about is the observed relative abundances of the light elements, such as hydrogen, helium, and lithium. These are the first three elements in the periodic table, and the nuclear physics that's required to predict how these form precisely matches the predictions of the Big Bang, and the observed abundances of these elements is a huge piece of evidence that gives us confidence in the Big Bang theory. Another one is the fact that our night sky is dark. Now, this is something we didn't talk about, so I'm going to skip over this one, but this is known as Olber's paradox, which if you're interested, you can look up, and it's evidence for a finite age of the universe. Also, some other data, which is it's not proof of the Big Bang, but it certainly is consistent with the Big Bang idea. For example, the oldest observable stars and galaxies are around 13 billion years. And this is consistent with the age of the universe, which is thought to be 13.8 billion years. So in other words, if we found stars or galaxies that were older than, say, 14 billion years, then we know something is wrong, because you can't have stuff inside the universe that's older than the universe itself. Okay, and so these ages here for the oldest stars and galaxies, it fits, very nicely with the age of the universe being 13.8 billion years. There are some other these so-called primordial hydrogen and helium gas clouds. This is something, this is additional physical evidence. We didn't talk about that, though, in this course, so let's not worry about this. And another one that, by itself is certainly not proof, but the fact that we see galaxies evolving tells us that the universe is changing. It's not static. And this is, of course, consistent with the idea of a Big Bang and a universe that is changing and evolving with time. So all of these things together indicate that the Big Bang theory has tremendous support from physical evidence. And that's what makes a theory strong in science. Okay, so that is it for part 1 of our lecture on cosmology. In part 2 of this lecture, we will finish off the chapter, and we'll talk more about modern cosmology and our universe. I'll see you then.